Today we have three talks. The first one will be over the node memory model for the AMD GPUs. Then we'll have GPU aware MPI and followed by affinity. These are all a little bit more complex topics. We'll be using some of the same examples that we did in the first day for the node memory model. So there's been several people who have contributed to this talk. I've reorganized it to try to make it a little bit more, a little easier to grasp. So I'm going to go over coarse and fine-grained memory. Going to go over atomics. Atomics, we do have double precision atomics in the GPU hardware. But they're a little more complicated than what you would have in a CPU. And I'll show you how to do page migration in HIP, and then how that affects our OpenMP implementation. So what is a memory model? You have to, especially with these fine-grained parallelism models, you need to know the rules for the synchronization of the memory, when it gets updated, when the other threads see it. If you don't understand this or aren't watching for it, you can get data hazards or race conditions where you get a wrong answer because one of the compute units doesn't use the updated value. These are particularly difficult things to catch when you're developing code. So, and then heterogeneous memory management is a feature of the Linux kernel. Basically, a pointer on the CPU is also a valid pointer for the GPU. And then you can migrate page between the CPU and the GPU. This makes it more convenient to do some programming on the GPUs. XNAC is a term on the AMD GPUs that controls whether the GPU retries memory accesses that occur due to a page fault, which means that the page of memory isn't on that device. And there's this is a key thing in the AMD GPU hardware. You can have three possible values for XNAC, and when you're compiling, you're going to want to consider what type of program you're running and what you want to support. So there's two possible ways to migrate pages. We can explicitly move them, or we can let it automatically move back and forth. So HMM is always needed for page migration, and to enable that, you have to set XNAC to 1, and in your application, when you're checking whether that page migration occurred, it's difficult to tell from the application level. So there's several different allocators in a GPU program, and there's two of them which allow page migration. So you can use the system allocators or HIP-malloc managed, and they behave somewhat differently. So this is something you have to keep an eye on when you're developing code for the GPU. So the malloc system allocator Um, if you initialize it on the CPU as in this program and do a vector add kernel, the first time you get a slower time as the page migration occurs, and the following times are then very fast. So in this example, you notice that we only allocate the memory on the CPU. The memory is automatically migrated. If we use a new, we're going to see a slightly slower time for the initial migration. And then again, we see a faster time when we use that memory again. So setting HSA XNAC to 0, no migration will happen. With XNAC equal 1, migration can happen, and it may, the performance will vary. So if you look at this example above, if we align the values differently, we get different timings. So but you have to be a little careful with the malloc, because if you don't have the right alignment, it may prevent page migration. I don't know if this has been improved or with later versions of ROCm, but you do have to watch for that with the malloc. And for that reason, HIP malloc managed is considered the more reliable allocator. And here we see the first time is a bit faster than the malloc call, and the following times are much faster, as we saw before. And again, so we can use the prefetch, async prefetch, to go ahead and get the memory ahead of time. At least at the time that this was written, it was not asynchronous, but there are plans to make it asynchronous in the future. So you can go either direction, from the CPU to the GPU, or the opposite. And you need to have HMM to have that working correctly. So nothing happens if HMM is not available. There is a call hip mem advise that you can set different characteristics to the memory. And so here's an example of it where we set it to coarse grain. And there's several other things you can do with hip mem advise. The low-level details on that are still being developed for these presentations. So for XNAC equals 0, we got 4 different ways we can allocate memory. As you recall from earlier, HIP malloc managed is the one we recommend, and that one has a that one will automatically migrate, but we have HSA XNAC equals 0. So in this case, it is not migrating to the GPU. The granularity is fine, and we see that if we try to allocate memory on the GPU for malloc, we actually get a segmentation fault. So you can see that the behavior is different depending on how you allocated memory. Now let's look at when we set XNAC to 1, and we see now all of these are, well, malloc and hip malloc managed are migrating memory. Hip malloc and hip host malloc are not. So some ways this makes sense. Hip host malloc is for the CPU, and it does not migrate. But you do have to keep this in mind, especially if you develop a code and you're not using a memory migration and then you go back to try using it. You need to make sure your memory is allocated properly. So here's an example of a program where we're going to allocate memory using HipMalloc. And if we compile this, it should run and report passed. Now we did HipMalloc on the for the memory, and then we're going to do a mem copy. So that's an explicit mem copy, and then we're going to use it in our kernel. So that's a standard programming where we're explicitly moving the memory. Now we want to convert over to managed memory. We're going to comment out that HipMalloc. We just have the malloc on the host. We're going to initialize that data, and then we're going to launch the kernel. So in this case, it's going to fail because we did not set xnac to 1. So we can set that variable and rerun, and the test should pass. And if we do the HipMalloc instead of the malloc call and unset the xnac variable, then the test will pass. If we go to HipMalloc manage, the test will pass. So when you're using managed memory or unified memory, it can be helpful for porting applications, but explicit memory management may be preferable for both portability with systems that don't have unified memory support, and the performance may be slightly better. Also, you avoid some of these possible memory migration errors that we've seen in the previous slides. So it's just less complicated if you're explicitly moving memory. Still, the convenience may be well worth those details. And for page migration, HipMalloc manage does give the best performance. Malloc mostly works, but we need to be careful about the alignment on the malloc call. And then we have 2 other calls which the pages do not migrate. And this is still early on with this more complex memory model with the MI250, the MI210. So we still need a lot more work on real applications using these features and what the performance implications might be. So this was just memory migration. So that's our first topic. Let's move on to coarse and fine-grained memory, which is a slightly different concept. And in the coarse and fine-grained memory, what we're talking about is the coherence, when the data for each thread gets synchronized and when you can access it from another thread. In GPU programming in the past, you basically needed to exit the kernel before you could be guaranteed that you had memory coherence between work groups. Within a work group, you could use a synchronization call. So with fine grain, you can get coherence within a GPU kernel. And that allows some more powerful synchronization capabilities. So we can synchronize while that kernel is running, but it does reduce the ability to cache the data. And so again, we have 4 different memory allocators, and we'll look at those each, but there are default characteristics of each of these allocators. So we see that 3 of them give us fine-grained memory, and 1 gives coarse-grained memory. So HIP-malloc will return coarse-grained memory, the others return fine-grained memory. So we can modify that characteristic using HIP-mem-advise. So if we want to use one of those other allocators, we can change it with a HIP-mem-advise call. Now we have to be a little careful. Not all of them can be all of those memory allocators. The memory that is allocated may not be able to be set with HIP-mem-advise. So let's look at, so there's actually a bunch of other settings that are available in the HIP memory mem-advise settings. So we we really haven't experimented a lot with these. So you can set, you know, different characteristics for the fine grain. And these have different implications for performance and for synchronization. So for coarse grain, there is no coherency, but the level of coherency for the fine grain can be modified by these flags. So here's a table showing if you set the memory from these different allocators with HIP-mem-advise, you can change some of the characteristics for some of the memory allocations. So, you know, we don't have a lot of experience with this yet on the performance, or you know, if there's some tricks we could use to get synchronization at a lower level that might help us with some algorithms. And so there's still a lot of work to be done to exploit this capability. Now, for most of us, we really, other than, you know, some performance behaviors, we're not going to really worry about fine and coarse grain memory, except for one situation, and that's when we have floating point atomics. And that's because of the coherence, the different levels of coherence that you get from coarse and fine grain. So there's a lot of hardware atomics for integers, single and double precision floating point for all the floating point types. And if you use those hardware accelerated versions to fine grain memory, they will silently fail. So you want to have coarse grain memory if you're using hardware accelerated atomics. So in the initial MI250 release, the compiler replaced all the atomics with compare and swap loops because they're safe. So, and just to avoid behavior that was unexpected, all the atomics were replaced by the compiler. So we're not disabling the hardware atomics, we're just not having the compiler use the hardware atomics. Now, compare and swap loop is slower than a hardware atomic, and so a flag was introduced, and This flag is got kind of a strange name. So it's unsafe floating point atomics. The atomics are safe if you have coarse grain memory, but it was named this to warn people that they needed to be aware that they could have silent failure on atomics if they were not careful. Um, and then there's also a call, unsafe atomic add, which is a hardware atomic add. And you can use that to force the hardware atomics. So from ROCm 520, that flag will force the hardware atomics to be used. Now we just upgraded LUMI to ROCm 520, so if you've been using atomics, you do need to pay attention to maybe a change in behavior here, and maybe tune your performance by using the unsafe floating point atomics. And so we do want to emphasize here that unsafe atomics are safe if you're using them with the right kind of memory. Integer atomics don't have this issue, so they're always based on the hardware atomics. And I'm going to talk about OpenMP and how this affects OpenMP in the next section. So here's the summary for the atomics on the coarse fine grain regions. So you can force the unsafe, you can force the hardware atomics where you choose to. So be aware of where you're using atomics and what kind of memory you're using for those atomics. If you are using atomics, this gives you some opportunity for some performance improvement with the ROCm 5.2 release. So what is the performance impact? We've talked a little bit about, that these details can have some impact on your performance. Well, this is just sort of a numbers taken from one of our test cases in one of the applications. So we see hardware atomics with fine and coarse grain, and the fine grain is faster, but it gives the wrong answer. So, and these are normalized to coarse grain hardware atomics with a value of 1. So a cast loop in this application was 39 times slower. And if you do the cast loop on the fine grain, it's even slower. So using the right kind of atomics and the right kind of memory can have a significant impact on performance. Now, this is one application. The numbers may be quite different for your application. So from 5.2 onwards, and we just got 5.2 on LUMI, you can use that unsafe floating point atomics flag, and that will force the compiler to use hardware atomics. And if you've allocated memory using HipMalloc, that will work fine. Be careful in other cases. You can use the HipMem advise with some of the allocators to change the characteristics of the memory allocated with those. If you use the unsafe atomic add function, you can force the atomic to be a hardware atomic. And this is only for floating point operations. Okay, so we've moved on to the last section, which is what does this mean when we're in OpenMP? So we basically have shared memory here with OpenMP. Coherence is really important in the OpenMP programming model. So here we use the AMD OpenMP compiler. This is the Clang or AMD Clang in the ROCm LLVM directory. We set the architecture type, and then we can set the XNAC or the HSA XNAC flag. And then we can see what happens by using this libomp target variable. And there's a kernel version of that and also a more detailed info version that uses a bit mask to identify what things you want to see. So our default mode, we are not setting any flags. We're not setting unified shared memory. The map is going to say that you're going to go ahead and do the memory copy for that kernel that is shown there in the pragma statement. Let's go ahead and put the unified shared memory here. Now we don't need that map variable. Okay, the map variable was causing that copy to happen. With unified shared memory, we don't need that. It will automatically migrate. Now I said we don't need it, but I'm going to show you that adding it has an impact. So the OpenMP isn't moving the memory, but now our operating system the runtime of the system is going to move that memory for us. If we use maps, the pages are switched to coarse grain. Now, so if we include that map clause, instead of fine grain, we're going to have coarse grain. The memory migration is still automatic. Now, if we remember from the earlier talk, if we're coarse grain, we can do atomics on it. So these things all work together in perhaps maybe complex ways. And so if you add that map back in, you will have coarse grain. You can do atomics on it. So we add that map clause back in, and so that A and B remain coarse grained for the rest of the time. So you see the second loop, we don't have that map clause. So they stay coarse grained. Now we got to be a little careful here because this is not standard OpenMP. This is an extension from OpenMP. And so writing portable code requires some consideration here. So if we have a subroutine call where we have, in this case, we've inserted an init call, A and B changes to coarse grain, and it's still sticky, it's still coarse grain. So whether you do that in a subroutine call or within the same functional scope, it doesn't matter. So here's a table showing the different behaviors that we get with the map clause. So map clause in unified shared memory switches it to coarse grain. If we do the target allocation, the OpenMP target allocator, we get coarse grain. And if we have pinned memory, we still get that memory pinned to that address, and it will not migrate. So now we use the fast floating point atomics, those hardware atomics. We're going to add this fast FP atomic, and we have a pragma call right here. And it will fail because we haven't done anything to make sure this is coarse grain memory. It's fine grain memory. Atomics, fast atomics will fail on fine grain memory. So if we add the map clause, now we've converted it to coarse grain, and we can use the fast floating point atomics. So we see here how we can make this work with the fast atomics by combining the behaviors of this automatic memory migration and using the map clause. We can force safe atomics. So if we didn't have that map, we can force that compare and swap loop instead of using that hardware atomic. So again, we have a table here showing how these all behave in different situations. So we have the safe, the unsafe. I really hate it when we have a double negative, a dash M, no unsafe floating point atomics. And then we show the hint clause value, and we can see that we can force different kinds of atomics in different situations. So in conclusion, with OpenMP, some of these behaviors are specific to the AMD GPUs. So these are extensions to OpenMP that you can fine-tune your application, but you do need to think about the portability of these. If you're going to run on other hardware, what's going to happen? And so we do recommend some consideration for that as you try to exploit these kinds of capabilities. So the memory model in general is more complex than perhaps you have seen in other GPU hardware, and we're still working on fully understanding how this should be used in applications. And we may see some changes in future releases as we tune that to be safe and fast for the majority of applications. Okay, with that, I am done with that section, and I'll open up for questions. That was all clear. I'm amazed because it's complicated.
So you mentioned that